There are a couple different ways that we can describe the location of electrons about the nucleus. One is electron configurations. This kind of gives us an overall view of where all the electrons are located, in which main levels and which sublevels are they located in. But there's another way that we can, pinpoint specifically an electron and refer to an electron, and this is through the use of quantum numbers. Now, just like you would address a letter or a package to somebody, you have to be very specific about the location. Just giving the state isn't enough. You have to give the city and the state. And even that's not enough. So then you need to give the street number. And if it's an apartment building, then you have to give the apartment building. So the more specific you get about the location, the more pieces of information that you're going to need to provide. For electrons, we can describe their location with a set of 4 quantum numbers. And the generic variables that we use to represent these are n, l, m, and s. And when we see a series of these numbers, they're separated by commas. And just like postal addresses, there are valid values and there are invalid values. If you put the wrong zip code down on a package and that zip code doesn't exist, it'll be returned as undeliverable. If you put down the wrong name on the package, it gets returned to sender. Okay, there's nobody here by that name. So there are certain values that you can have for each of these 4 slots. Now the first number at the very beginning, the n, is known as the first quantum number or the principal quantum number, and this simply represents the main energy level. If we think of the Bohr model, the planetary atomic model, this would be analogous to the rings about the nucleus. Now, n can be any positive whole number. Right? So any positive whole integer, 1, 2, 3. Realistic, in theory, it could go up to infinity as long as it's a positive whole integer. But in reality, currently, we only go up to level n equals 7. As we get more elements that require more electrons, eventually we may have an 8th main level, but for right now, we only go up to 7. Once we get into the main energy levels, we see that we can further subdivide those into sublevels, and each sublevel has a slightly different energy to it. So as these fill in, we need to identify which sublevel is going to be filled in first and then second. And so this L, the second quantum number, describes which of those sublevels we are referring to. The least energetic of those is the S sublevel. Now, an S sublevel has a specific L value. Whenever you see an L value of 0, that's referring to an S sublevel. P sublevel, the next most energetic type, has an L value of 1. D sublevels would have an L value of 2. And if you follow the pattern that's being established here, the 4th type of sublevel, F sublevels, would have an L value of 3. And again, as we add more sublevels, the pattern should continue to L equals 4, L equals 5, but currently 0 to 3 is all we have need for at the moment. So those are the valid values that we have. If we're going to define the possible values, the legitimate values we could have for an L number, we need to keep in mind that there is potentially an infinite number of main energy levels, and if you look at the way that the sublevels are divided, the first main level has only an S sublevel, so the only possible level that you have is a 1S, and so to refer to that, you can only have an L value of 0. If we look at the 4th main level, n minus 1 give us 3. So L is going to have values anywhere from 0 up to and including whatever n happens to be for that particular electron, for that particular situation, n minus 1. Once we're into the sublevel, now we have to talk about which individual compartment are the electrons going to be in, and this is where the concept of orbitals comes in. Each of the different sublevels can hold a different capacity of electrons, and the orbitals are the designated area of space where one pair of electrons is going to reside. S sublevels have one orbital, P's have 3 orbitals, D sublevels have 5 orbitals, and F's have 7. In parentheses, you see the maximum capacity of the electrons total that there would be. Now, to reference which of those orbitals, for an S sublevel, it's easy. There is only one orbital. But for a P, or a D, or an F, you need to be able to identify one of those 3 for a P sublevel, one of the 5 orbitals for a D, one of the 7 for the F. And the way that we do that is with that third principal quantum number, labeled M. Now, in terms of labeling the actual orbitals, if you have an orbital diagram, probably the easiest way to label them in terms of their numbers is start with the very middle orbital. If you think about it, these are all odd numbers, so there's always going to be a center orbital, and then you'll have equal numbers of orbitals on either side. Start with the middle one, number it as 0, and then count your way out in either direction. Negative to the left, positive values to the right. And what you'll find is that your M range goes from negative of your L value to positive of your L value. So take, for instance, a P sublevel. You've got 3 orbitals, 3 spaces, 3 boxes that you would be putting electrons into in an orbital diagram. And we need to label each one. Well, the center one is going to be labeled 0, and you've got 1 on either side, so you've got -1 and +1. Well, if you think about the L value associated with a P sublevel, L is equal to 1. So in a P sublevel, with its 3 orbitals, you would label those orbitals -1, 0, and +1 from left to right. For a D sublevel, L equals 2. So when you label those 5 individual orbitals, starting at the very left, you would have -2, -1, 0, +1, and +2. And that pattern works for the F sublevels as well. Now, as we're adding these electrons in, okay, it's helpful to maybe put it in terms of something we can relate to. Finicky hotel guests. All right, the ones that go and they want things their way. They're very picky about their stay. The electrons are going to want the best possible locations, right, as they come into the atom. So they're going to fill them in from best possible accommodations to the least, the least favorable accommodations. Now, in electron terms, what this means is energy. Okay, the locations that are filled in first are the least energetic, the closest to the nucleus. So the lowest level in the hotel, if you will. All right, and then they fill in on up. So first floor, second floor, third floor, first energy level, second, so on and so forth. This is known as the Aufbau principle. It not only applies to main energy levels, but even within those main energy levels, the sublevels, the distinction in energy that each of those sublevels, S is always the least energetic, P followed by P, then D, then F. Aufbau also governs how the electrons will fill in those sublevels. Once you're within a given sublevel and you're looking at those individual orbitals, think of the orbitals as being like a bunk bed in the room. The sublevels would be the individual rooms on the main floors, and those orbitals are like bunk beds. Well, anybody going into a room, if they see an open bed or an open bunk, one that nobody else is even at top or bottom yet, they're going to go for that one 9 times out of 10. So the electrons, as they go into a sublevel with multiple orbitals, the electrons are going to fill in 1 to an orbital. Then they'll go back as needed and governed by the Aufbau principle and double up. Okay, so at most you can end up with 2 electrons per orbital. Now, the 2 electrons per orbital, at this point we've got 2 of these particles, both have negative charges, and they're in very close proximity to one another. Going with the hotel analogy, they're in the same hotel, they're on the same floor, they're in the same room, and they're in the same bunk. Okay? But again, they're both negatively charged. There's going to be a lot of repulsion there. Okay? And we can't have that. So we require that 4th quantum number. And when it comes down to it, when you're talking about two electrons, if they are very close to one another in proximity, their addresses are going to be very similar. It's only going to be in the last digit that you have any difference. And so what the Pauli exclusion principle, which is another governing principle, says is that no two electrons in an atom are going to have the same set of 4 quantum numbers. There's another way of referring to this, and we'll get to that on the next slide here. But if we think about it, all right, principal quantum number can be the same for 2 electrons easily. What that is actually going to translate to in terms of our visualization of the electron cloud is how big the cloud is. The L describes the shape of the cloud, the type of sublevel. S's have a spherical shape, P's have a dumbbell shape lying on the axis, D's are double dumbbell shape, usually lying between the axes, and then F's are, you got a combination of dumbbells and rings and all different combination of funky looking clouds. The M, the orbital designation, is going to be the designator for the orientation in space. So for instance, the 3p orbitals, the -1 oftentimes is referred to as the px orbital. It's the dumbbell shaped orbital that lies on the x-axis. The 0 orbital, the middle one, is sometimes referred to as the py orbital. And the one that's the +1 value for M is referred to as the pz orbital. And so that would be your dumbbell shaped orbital lying on the z-axis. So the third quantum number tells us how are these electron clouds oriented. So it may come down to that last quantum number to indicate or differentiate one electron from another. And so the S makes it easy to remember. S represents spin. When we think about the electrons that are in the same orbital, they've got like charges. If you think about two magnets, right, and you have their polarities aligned and you bring them close to one another, they're going to repel. But if you invert one of them, now the norths and the souths match up and attraction occurs, and they can exist in the same vicinity. Electrons are much the same way. And the way that we think of their charge fields being able to be inverted from one another is by thinking of them having opposite spins. The Earth rotates, all right, and then the composition of the Earth creates a magnetic field. Okay, so depending on the direction of rotation, plays a role in terms of the orientation of the polarity of the charge. So we describe the spin of the electron either clockwise or counterclockwise, and we refer to electrons with a clockwise spin as spin up. If we're drawing an orbital diagram, that would be an up arrow. The S value we correspond to that is a +1/2. It's the only one of these values that we talk about that isn't an integer. If it has an opposite spin, if it has a counterclockwise spin, we refer to that as a spin down. That would be a down arrow in your orbital diagram, and the quantum number would be a -1/2. So to review, okay, the 4 quantum numbers and their possible legitimate values. N, the first one, is your principal quantum number. It's the main energy level number. Could be anything from 1 to infinity as long as it's a positive whole number. In reality, right now, we only have 1 to 7. The second quantum number is L. Legitimate values run from 0, which would be an S sublevel, up through and including n-1, n being whatever the principal quantum number happens to be for that particular particle. The third quantum number is M, which refers to the orbital, which tells us about the orientation in space of that cloud. Its legitimate values run from the negative of the L value through the positive of the L value for that given particle or that given sublevel. And finally, the S, the spin quantum number, it only has 2 possible values, either +1/2 for a spin up electron or -1/2 for a spin down electron. So if we take a look at some examples here, all right, first example, hydrogen has 1 electron. So according to Aufbau, the lowest possible energy level, sublevel could go in is the 1s level. And there's only 1 electron. So the principal quantum, or the quantum number address for this electron, start with the main level, so it's 1. It's an S sublevel. For S sublevels, L equals 0. So 1, 0 is going to be the first 2 numbers in the address. The third one tells us about the orbital. And there is only one orbital. Remember, we always start in the middle with 0 for our numbering. So 1, 0, 0 tells us 1s level, middle only, orbital. And it's a spin up. It's an upward facing arrow. So we give that an s value of plus 1/2. If we take the second electron, okay, which will go in for helium, okay, so this electron here, again, it's the 1s level in the sole orbital in that 1s level, so 1, 0, 0, but this time it's spin down, therefore the address would be end in a negative 1/2. All right. Notice if we had done the other electron in the helium, the spin up in the 1s, its address would be identical to the one that we had for the hydrogen. But that's okay, because if you notice, they're the exact same electron. Okay, so you would expect them to have the same address. All right, lithium, 2s sublevel with a spin-up electron, and again, in the only orbital that's there, so the quantum number address would be 2, 0, 0, plus 1/2. Right, because you got the upward facing arrow, so it's going to be plus 1/2. All right, nitrogen. Now, we've got a 2p sublevel, 3 orbitals, and there's 1 electron in each of those orbitals. Remember, they're going to want their own bunk before they choose a bunkmate. Okay, I forgot to mention it before. That rule where you go 1 electron to an orbital before you pair up, that's known as Hund's rule. Okay, Hund's rule, H-U-N-D. All right, so if we take a look at this electron, the very last one, p sublevels have 3 orbitals, so 2p would have the quantum numbers 2, comma 1, okay, because for a p sublevel, L equals 1. Now, remember how we number the orbitals, the spaces for the electrons. 0 is always the center one, and it's symmetrical on either side, negative numbers to the left, positive to the right. So our orbitals, in order, would be numbered -1, 0, and +1. The electron of interest is in the +1 orbital. So our address, and it's spin up, okay, so our address will be 2, 1, 1, plus 1/2. Remember, each part of that quantum number address tells you a different piece of information about the residency of the electron. Main energy level, sublevel, orbital, and spin. For oxygen, if we take a look at this electron, again, it's in the 2p sublevel, so 2, 1, it's in the first orbital of the 3, so this would be -1, and it's spin down, so this would be -1/2. So if you keep in mind what the limitations are on each of the principal quantum numbers, okay, and you apply those guidelines, you should be able to identify and map out the location of any electron, no matter how many there might be. Because again, a quantum number set is specific for one specific electron and its position.